Good morning, students. Dear students, as in the previous video, we had discussed about the that is part 7 of chapter 5, that is laws of motion. We had discussed about law of conservation of momentum, and in the law of conservation of momentum, we had discussed the derivation regarding the law of conservation of momentum, and one numerical we had solved that Newton's third law is contained in Newton's second law. All these things we had discussed in that chapter, that part of the video lecture, that is chapter 5, law of motion. Now, today we are going to discuss one numerical based on the conservation of momentum, and after that we will discuss about the next topic, that is equilibrium of forces, and in that we will discuss about concurrent forces. So let us discuss on this numerical. The numerical is in front of you here. The numerical says that a moving neutron with the speed 10 to the power 6 meter per second. The neutron is moving with the speed of 10 to the power 6 meter per second, collide with the deuteron. Deuteron, that is isotope of hydrogen, which is at rest. And so let us draw the diagram. A moving neutron. Suppose this is the neutron. This is neutron. Neutron, and this neutron is moving with 10 to the power 6 meter per second. Next, it collides with a deuteron. This is a deuteron. And it is at rest. This deuteron is at rest and sticks to it. This neutron, when collides with the deuteron which is at rest, the neutron sticks to this deuteron. They both going to stick with each other, and after collision, find the speed of the combination with the mass of neutron and deuteron are this and this much respectively. When this neutron is going to strike this deuteron, they are going to stick with each other. They are going to stick with each other, and they start moving with a common velocity. So we have to find the speed. We have to find this common velocity. Mass of neutron it is given. Mass of neutron is given 1.67 into 10 to the power minus 27 kg, and mass of deuteron it is given 3.34 into 10 to the power minus 27 kg. Both the masses have been given, and we have to suppose this mass is m1, which is equal to 1.67 into 10 to the, and this mass is m2, which is equal to 3.34 into 10 to the power minus 27 kg. Now both m1 and m2 are going to stick with each other and move with the common velocity. Now we have to find out this common velocity. So for this we have to apply the principle of conservation of momentum. Applying principle of conservation here, applying principle of conservation of momentum, because what you are saying that there is no external force being applied. Whatever the force is applied is by m1 on m2 and m2 on m1. These are the internal forces, so they cancel each other, and net external force on this system, isolated system, is 0. So we we apply conservation of momentum here. And when we apply the conservation of momentum, then m1 plus m2 u2, it is equal to m1 plus m2, because both the masses are going to stick with each other, and this is the final velocity v. That is the final velocity v. Now put the values and get the answer. Now look at the experiments. Now we can put the value m1, it is given as 1.67 into 10 to the power minus 27 into, that is kg, into 10 to the power 6 meter per second plus m2 3.34 into 10 to the power minus 27 kg, and m2 is at rest, that is equal to 0 meter per second. That is equal to 1.67 into 10 to the power minus 27 plus 3.34 into 10 to the power minus 27 kg into v. So this will give the value 0, and we will get 1.67 into 10 to the power minus 27 into 10 to the power 6 kg meter per second, and here 1.67 plus 3.34 into 10 to the power minus 27 into v. This is kg and this is v meter per second. So 1.67 into 3.34, that is 5.01 into 10 to the power minus 27. Now it is equal to 1.67 into 10 to the power minus 27 into 10 to the power 6 kg meter per second upon 5.01 into 10 to the power minus 27 kg, and this is equal to v. Now this will cancel it out, and it will become, the result will become 33.33 into 10 to the power 4, 33.33 into 10 to the power 4 meter, kg cancel out, meter per second. V is equal to 33.33 into 10 to the power 4 meter. This is the final velocity with which, this is the final velocity v, with which both the deuteron and neutron, which are combined together, after combination they will move with this common velocity, that is 33.33 into 10 to the power 4 meter per second. So now this is all about the conservation of momentum. We have discussed the numerical also. Now we are coming to our next topic. And the next topic is equilibrium of forces. Next topic is equilibrium of forces. Equilibrium of a particle. Equilibrium of a particle. First, on discussing equilibrium of particle, first let us understand what are concurrent forces. What are concurrent forces? So first we will define concurrent forces. What are concurrent forces? Concurrent forces. As in the previous classes in mathematics, you had studied about concurrency, and based on that concurrency, here the word concurrent. And concurrency or concurrent means to say that if anything is acting on a single point, means if the forces are acting at a single point, if forces are acting at a single point, then these are called as concurrent forces. These are called concurrent forces. So we can say that if the forces are acting at a single point, if the forces are acting at a single point, then that forces are called as that forces are called as concurrent forces. That forces are called as concurrent. And when these concurrent forces are in equilibrium, when these concurrent forces are said to be, when these concurrent forces are said to be in when these concurrent forces are said to be in equilibrium. So these concurrent forces are said to be in equilibrium when the resultant of these concurrent forces are zero. When the resultant of these concurrent forces are zero, then how can you justify the resultant of these concurrent forces are zero? So here we have drawn the two cases. This is case first and this is case second. Now, from these two diagrams, we clarify why these concurrent forces or how these concurrent forces are in equilibrium. So first, so when these concurrent forces are said to be in equilibrium, these concurrent forces are in equilibrium when their resultant is 0. When their resultant is 0, when the resultant of these forces is 0, then the net force acting on the system of forces is equal to 0, and in that case we can say that these concurrent forces are in equilibrium. Now we will discuss it one by one. For two collinear concurrent forces, how it is in equilibrium. For two collinear, so this is first case. Case first, for two concurrent forces, for two concurrent forces, and for two concurrent forces they are in equilibrium if F1 is equal to minus of F2. Means both the forces are equal and opposite. Means both the forces are equal and opposite. And from here we can write it as F1 plus F2 is equal to 0. Means the net resultant force in this case is 0, and these forces are said to be concurrent and equilibrium. Concurrent, these forces are said to be concurrent forces, and they are in equilibrium. Now for three concurrent forces, the second case is for, we had discussed for two concurrent forces. Now we will discuss for three concurrent forces. For three concurrent forces. Second case, for three concurrent forces. So for three concurrent forces we are taking two forces. The point is, this is OA, this is OB, and this is OC. This is OC. And we can write the name of these forces, that is F1, F2 and F3. F1, F2 and F3. Now look at it, these forces are inclined with on each other at an angle. Suppose this angle is gamma. Alpha, beta and gamma. Alpha. These are inclined with each other at three angles, that is alpha, beta and gamma. And we have to discuss for three concurrent forces. So we have to find the resultant force, that is OC dash. We have to find the resultant force, that is OC dash, which is opposite, equal and opposite, and this OC dash is the resultant of OA, and that is F1 and F2, and it is opposite to OC, that is F3. So concurrent forces, and they are said to be in equilibrium if the force OC dash is equal to the force OC. Means these forces becomes equal and opposite, and the net effect of these, the resultant of these two forces, that is OC dash and OC, is equal and opposite, and they are going to cancel each other, and net force at point O is equal to 0. Then these three forces F1, F2 and F3 are said to be in equilibrium. So I had explained it. Now mathematically I am going to give the relation for this. So for three concurrent forces F1, F2 and F1, F2 and F2. So F1 plus F2, F1 plus F2, that is equal to minus of F3. F1 plus F2, that is equal to minus of F3, or you can say that F1 plus F2 plus F3 is equal to 0. F1 plus F2 plus F3 is equal to 0. So, three concurrent forces are in equilibrium when the resultant of any two of them is equal and opposite to third force. So, three concurrent forces are said to be in equilibrium if the resultant of any two of the forces is equal and opposite to the is equal and opposite to the third. Let's here look at here. The resultant of OA and OB is equal and opposite to the third force F3. So we have to get it as the resultant of F1 plus F2 is negative of F3, or you can say that F1 plus F2 plus F3 is equal to 0. Then the forces F1, F2 and F3 are said to be in equilibrium. So here we have discussed about three concurrent forces. Now we are going to generalize the above concept for n number of forces. So, in general, now dear students, here I am going to give you a very good concept. Suppose here there is force F1, here there is force F2, and here there is force F3. And if I am saying that, if F1, F2 and F3 are in equilibrium, then if these are three forces and they are in equilibrium, then they can be represented by the sides of the triangle which are taken in the symbol. This can be represented by the sides of a triangle or a closed figure or triangle, because they are three forces, so we can represent it by the sides of the triangle taken in same order. So this is A, B and C. then we can represent it as F1, F2 and F3. So dear students, there is a question in your mind, sir, how can you be able to do this? Suppose if they are the two forces, then F1 and F2, then their resultant is represented by, if they are triangle, then their resultant is represented by this. Clear? Then look at it. If we are making the triangle, if we are transposing the vector to this side, then suppose this is one force, this is F1, this is F1, this is F2, and this is F2. So from here you can write it as F1, F2 plus F3 is equal to F1. Or F2 plus F3 is equal to minus of F2. So in this way you can write it as, but now we have done what? If F1 and F2 are in this way, then we can draw the resultant of this by taking the side of the triangle opposite to this in this way. But since they are in equilibrium, so we have drawn its reverse, that is minus of F3. And so it can be represented by the closed side of the triangle. So if the three forces are in equilibrium, then we can represent it by the sides of the closed triangle. If four forces are in equilibrium, if suppose four forces are in equilibrium, if four forces, then it can be represented by the sides of the parallelogram taken in the same order. So in this way we can represent the forces or vectors which are in equilibrium by the closed sides of the polygon. Closed sides of the polygon whose sides are taken in the same order. Now we are going to generalize the formula what we had studied. Suppose n number of forces are acting on a part. Suppose n number of forces are acting on a part. If n number of forces are acting on the part, and these forces are in equilibrium, then that forces can be represented by sides of closed and sided polygon. Then they can be represented by the sides of the closed and sided then they can be represented by the sides of a closed and sided polygon in such a way that F1 plus F2 plus F3 plus F4 plus Fn is equal to G. This is the condition for equilibrium for n number of forces. Now while saying F1, we can write it as F1x plus F2x plus F3x plus up to so Fn x equal to G. Means all the x component of force, if they are in three-dimensional, if these forces are acting in a space, then the component of forces, the sum of all the component of forces of F1, F2, F3, F4, Fn which are acting in x direction, then F2, F1y plus F2y plus F3y plus F and y is equal to 0. Similarly, F1z plus F2z plus F3z plus up to so on F and z is equal to G. Means if F1, F2, F3, Fn, F1, F2, F3, Fn, these are the forces which are in equilibrium but acting in a space. So if they are acting in a space, then we can resolve the force F1 into its three components, that is F1x, F2x, F3 and Fnx. Similarly, F2x, F1y, F2y, F3y, Fny. Y component, F1z, F2z, F3z, Fnz. Z component means all the x, y, z component of the forces can be summed up and it is equal to 0. Then this is the generalized concept of equilibrium of forces which are acting in the space. So this is all about the equilibrium of forces. Now we will discuss about Lame's theorem. In the next video we will discuss about Lame's theorem and numerical based on it. So that's all for today, students. Thank you and have a nice day.